Okay. You guys don't want to see that. Okay. The other thing I want to do is I want to put up the chat. All right. The people who are doing stuff online, oh, what? Where did Zoom go? Where did you go? Want the chat? You can put stuff in the chat if you have questions you want to ask as we're working along. If you guys have got questions. All right. This is a revision seminar for Maths for Data Science in semester 2, 2025. My name's Nicholas. So I'm happy to do almost anything. Usually what we do is we go, hey, what would you like to do? So suggestions. So I'm going to point out the fun thing that someone left behind for me. So someone very carefully, I'm going to assume they mean they spotted an owl and Taylor series. We can do Taylor series. We can do the spotted owl is I think a reference to Markov chains. And so we can do a couple of examples and talk about the sort of things you might see in the exam from that. One of the other students I've talked to has sort of suggested that maybe what we could do is look at some of the practice problems you were given and look at some of the harder ones, or talk about those concepts in a way that might actually be helpful for trying to sort of what you might see in the prepare for an exam type of thing. Okay. So, like I say, this does work better if you ask me questions. All right. The other thing I want you to do is point out when I've done something stupid, like forget to make the camera show the thing that's on the screen. All right. Because what's on the screen should be what I'm recording. Okay. So I want that recorded so that people can see what's going on. Okay. So, all right, sweet. Okay. So eigenvectors, eigenvalues, mainly specifically on the assignment. I'm aware we can't discuss the assignment. Yeah, look, with some of these things, it's like, I'm going to talk, like eigenvectors and eigenvalues almost always appear. All right. So maybe what we're going to do is we're going to start with talking about eigenvectors and eigenvalues. So let's see. So that could be really annoying. And that is just a little bit in the way. Let's try and put it up in this corner so it's not so much in the way. Sweet. Okay. The lag on that is going to get really irritating. That should work a little bit more. Okay, so first thing we're going to so much of what can happen with eigenvectors and eigenvalues can be covered by just remembering how we define them. We have said that A times some vector is equal to lambda times some vector, right? So where lambda is a real number. Yes. This is so laggy. I know it is irritating the crap out of me too, but also there is very little I can actually do to make it happen. Yes. So there is not much I can do about the extreme lag in the system. Yeah. What's that? Oh yeah. No, you mean on my system or the yes, so yeah. It's to make it use this document camera. Or this is actually just an ordinary webcam, but you know, hey, talking of which, we're about as sharp as we're going to get. It's going to be really impossible to. It's actually because we're actually, come on. So painful. Um, count to 10, beautiful. Okay, so what we're saying about eigenvectors and eigenvalues is they come back to this defining characteristic. Okay, so we can actually rewrite that. So I like to go AV minus lambda V is equal to 0. All right. Now, I'm going to shove my I in here. And this, so what we're actually getting, all right. So we're actually solving this system. All right. We're going to try and solve the system where we've got A minus lambda I times V is equal to 0. Bear in mind, I don't want the 0 vector. Because this is a homogeneous system, I don't want the 0 vector. So I want anything but the 0 vector. And so that's why we go through and we go, actually, if I go A minus lambda I is equal to 0, then that's going to get me values of lambda such that that system will have infinitely many solutions. And infinitely many means there must be non-zeros. All right, so key part, going to give me non-zero solutions. So everybody loves this. And then once we've gotten, so we're going to solve this. And then once we've solved our system, we're going to try and use each of those lambdas. All right, we should. Did I write one out? I did actually. Sweet. Okay. So what I'm going to do is we're going to try. We're going to try and do that. So typically they will tell you. So an exam question might actually go, here's a matrix, here's a vector, verify that this thing is an eigenvector. So in this case, it might go, all right. This means do the multiplication. Yes.
Sorry, this formula doesn't look the same on the lecture. My lecture is
Thank you. Well done. This does not look like what you get in the lecture. So what you would have got is you would have got lambda I minus A equals 0. Yeah. And so see how I did this? If I'd done lambda I V minus A times V is equal to 0, then my matrix would have been A minus lambda by V is equal to 0. Now, so I could never remember which way round I was supposed to do it. I have a problem with sort of trying to put things in the wrong order all the time. And then I've discovered it doesn't matter. All right. So the beautiful part about this is because I want it to be 0, this is basically minus this. All right. And so because of that negation thing happening and it being equal to the thing I want it to be equal to 0, I don't care. All right. And it actually won't change what the eigenvectors are either. Okay. Because I'm basically the solutions to this are the same as the solutions to the original thing. All right. So, and they're equivalent to the way I do it. And so, for me, admittedly, the thing I used to do is it means that when I'm doing that determinant to work out what the eigenvalues are, there's less minus signs. And less minus signs means less minus signs to forget. So I can get it right every time. So verify this is verify an eigenvalue. All right, it really is just doing the multiplication. All right, I'm gonna see how much of it you can get done before it catches up with me doing the working. All right, this is going to be really easy because it's like 0 plus 0 plus 0, and then 0 plus 0 plus 0. All right, and 0 plus 0 plus 5. So when it's saying verify this is an eigenvector, I want to be able to go, hey, that can be written as 5 times the very vector that I started with. So this thing here and this thing here are the same thing. And so this must be my lambda. All right. Now, next thing is find the other two eigenvalues, right? It's a 3 by 3 matrix. There must be 3. What is the trick I'm going to use to find my other two eigenvalues? Trace and determinant. Trace and determinant. All right, we know trace of my matrix is sum of determinant of the matrix is equal to all right. So now I'm going to move that up a little bit. Oh, that's really annoying. So my trace of this matrix is going to be 2 plus 2 plus 5. 2 plus 2 plus 5, which is equal to 9. Sweet. And my determinant of that matrix, I'm going to do a thing where I move along the bottom row. So it's going to be equal to like 0 by subdeterminant. Take out the row, the column, that would be a 3, a 2, a 0, and a 0, plus, actually, minus. 0 by the subdeterminant would be 2, 3, 0, and 0. All right. Plus 5 by 2, 3, 3, 2. All right. Everybody's loving that because that's working out for me. It's 0. I don't even care about it. So this is going to be 5 by 2 times 2 minus 3 times 3, which is equal to 5, 4 minus 9, which is equal to minus 25. Sweet. All right. So I've got my values. So I'm going to go like lambda 1 plus lambda 2 plus the one I know, 5, is going to be equal to 9. And lambda 1 times lambda 2 times, we should say 5, is equal to minus 25. And so that's going to tell me that lambda 1 times lambda 2 is equal to minus 5. And that's going to tell me that lambda 1 plus lambda 2 is equal to 4. All right. So if you don't happen to have already seen the answer, all right. So sometimes I think it might be I do this often enough that I can go, hey, that's what the answer is going to be. We're not going to do that. So we're going to go, all right. I'm going to maybe rewrite this to say lambda 1 is equal to 4 minus lambda 2. And so when I come down to this one, I'm going to go 4 minus lambda 2. Lambda 2 is equal to minus 5. little bit of expandy. So I'm going to get minus lambda 2 squared plus 4 lambda 2 is equal to minus 5. I am going to put everything over there. So I'm going to write this as like 0 is equal to lambda 2 squared minus 4 lambda 2 minus 5. And it's going to factorize lambda minus 5. Really? Sure. Lambda plus, yep, no, minus 5. Lambda plus 1. Okay, sure. Did I really get that right? Sure. Is equal to 0. All right. So, okay. So my eigenvalues, lambda is equal to 5, minus 5, and 1. Can't help feeling like I made a mistake there somewhere. Did I? Pause momentarily. Plus 4, did that right. Did that right. We're going to change that so that says 25 like I meant to, right? Ah, man. You guys got to watch me, all right? I say the right thing, I write the wrong thing, or vice versa. So, this is why I'm going, I thought the other eigenvalues were going to be 5 and minus 1. Yeah, I've done something wrong. I have definitely done something wrong. I did that right. Tick. Tick. Did this. And so that should have been that. Why did I? Oh no, that should be minus 5. Don't you hate it when you've gone, no, that just doesn't feel right? Let's pretend for a second, shall we? This is saying that if I try lambda is equal to minus 5, if I go back up to my defining characteristic, if I go up to that a minus lambda I by v is equal to 0. Ooh, more people, or alternatively, people signing in again. So I should be able to do, so if lambda is equal to minus 5, this should be 2, 3, 3, 2, 0, 0, 5, 0, 0. Something has gone terribly wrong. We're going to go minus 5, minus 5, minus 5, 0, 0, 0, 0, 0. And that should get me minus 3, 3, 0, 3, minus 3, 0. And that should be a 10. And that's where my problem, that's why I'm going, oh, okay, sure. And so if I do my row operations on that, so let's write this out, minus 3, 3, 0, 3, minus 3, 0, 0, 0, 10. All right. So I want to make, I'm sort of solving for where this is equal to 0. All right. Going to go through, do my row operations. And so I'm going to do like row 1 is equal to minus a third, row 1, row 2 is equal to a third, row 1, and row 3 is equal to a tenth. That's a 3, that's a 10. Row 3. All right, so that should be like 1, minus 1, 0. That should be 1, minus 1, 0, 0. And that should be 0, 0, 1. All right. Sweet. That's terrible, but we're going to pretend I did that right. All right. And so when I come to doing this, all right, the reduced row echelon form of this is going to look like, all right, I'm not going to worry too much about hopefully at this point in time, you guys all got that, right? And so I'm going to identify my basic variables. And so one of them says like x3 is equal to 0. And this one says x1 minus x2 is equal to 0. So x1 is equal to x2. And so my eigenvector would be like 1, 1, 0, x1. I can kind of forget about that because that's going to help me define the eigenspace. All right. So we know the difference between eigenspace and eigenvectors. Vectors are elements of the eigenspace. The space describes the whole set of them. All right. This is, so part of the reason why I'm going, I'm sure I've made a mistake, but like, I did. Yes. I still can't, it's bugging me a lot because I'm like, no, my eigenvalues should be 5, 5, and -1. And somewhere in there, I've made a mistake and I can't pick it. Mm. Oh, you're an idiot. Can I go back here? I'm going to wait for a second. All right, beautiful. All right, sweet, on fire. So, good. We should be quite clear that I actually didn't do -5 in this calculation. I did that. Oh, man, there are things. Joined, left, joined, left. Okay, so we can do that. We can definitely do this. Sweet. Ah, man. We should go definitely plus. Definitely plus. All right. There are days. Okay. Same plan should work. So if I go and do if I go do the other one, lambda is equal to -1, and it should be working this way. 2, 3, 0, 3, 2, 0, 0, 0, 5, minus -1, -1, -1. Should get me, that should be 3, 3, 0, 3, 3, 0, and 0, 0, and 6. Sweet. I'm not going to bother with the showing you the row reductions. Row reduced form of the augmented matrix. That is telling me that x1 is equal to -x2 and x3 is equal to 0. All right. Corresponding to the eigenvector 1, -1, 0. Okay. Okay. So that is how we go about doing this. All right. Everybody happy with it, right? So what else could we do with eigenvectors and eigenvalues? All right, so I'm going to come back and focus on a couple other things. I'm going to actually just pause momentarily to actually, because I made this up as I'm going along, right? Going to point out, see how this third column is a constant multiple of the same column of the identity. All right, this is a thing we do a lot when we're writing exam questions. Is we'll put in one of the columns of the matrix as a multiple of the corresponding column of the identity, and that tells me that that number is an eigenvalue, and moreover, that the associated column of the identity matrix will be an eigenvector. All right. So when I thought about writing this matrix out, I thought, if I do that, I know I will get an eigenvalue of 5, and that sort of 0, 0, 1 will be an eigenvector. All right. And you'll see that's exactly where I started this question. Okay. So that's the sort of thing that you can help to know when you notice these things can help you reduce the amount of work you have to put into doing the question. All right. So that's one thing. So the other question I've seen possibly this is um on the difficult end for what you guys do, right? But this is completely doable. All right. If we consider so V1, we're going to say suppose V1 is an such that B times V1 is equal to lambda 1 V1. All right. Because we're told it has eigenvalues, we can take a guess. We can give an arbitrary name to the eigenvalues, eigenvectors. Yeah. Sound like a plan. Now, I'm going to take this. If I've got B times V1, that is equal to lambda 1 V1. Maybe if I try and sneak a B in here, this would get me B squared V1. And this would get, so lambda is a constant, so I can actually pull that out the front. But I've said that BV1 is equal to lambda, so I can write this as lambda 1 times lambda 1 V1. That's not very tricky at all, is it? But so I can know, if I know the eigenvalues of a matrix B, I can know the eigenvalues. It actually works, and you can sort of see from the way that's done, any power of that matrix B, I can know the eigenvalues of. It's kind of cool. And it also implies something else, doesn't it? It actually says the eigenvectors of the matrix B are also the eigenvectors of the matrix B squared. All right. Sweet. All right. Beautiful. Okay, so this is something we can definitely do. All right. So that's kind of fun. Okay. Why do we care? All right. Why do we care? So I'm going to refer back to spotting an owl. The spotted owl thing is about Markov chains, right? And so Markov chains is one of those things where if you look at what you've got, so we usually say that, like, for a Markov chain, an plus 1 is equal, let's try that again. Vk plus 1 is equal to a times vk, where vk is a state vector. Okay, telling me about the number of people in there. So there's a couple of things about the Markov chain, all right, or Markov process. They may actually get you to create the actual matrix. I'm not going to go into doing that today. Been there, done that. Lots of videos are, so there's a lot of revision seminars for various subjects that we've done on our website. This one will go there as well. So I'm not going to go into this, but I'm going to talk about the steady state vector. All right, so my steady state vector, V, and they quite often do V star, is such that V star is equal to A times V star. Or maybe if I write that around the other way, A times V star is equal to, and I'm going to say 1 times V star. All right. This is exactly the same property as the eigenvector property with lambda is equal to 1. So all right. So we know it's going to happen. All right. Yep. And so if I was to get myself a matrix that has, I am going to pretend I haven't actually done the working on this one ahead of time. In fact, I haven't done the working on any of these ahead of time. I did get myself a Markov matrix. So sweet. All right. So to find my system, what I should be looking at is like A minus I by V is equal to 0. All right. Because we know the way we set up the Markov chain matrix, transition matrix, is guaranteeing that lambda is equal to 1 is an eigenvector. It is an eigenvalue, sorry. And so there must be an eigenvector associated with it. And so I don't need to do this. I can just go, hey, I'm just going to work out what that is. I don't need to work out the eigenvalues first. I can just jump straight into this. All right. And so when I do this bit here, so I'm going to have my 0.1, 0.3, 0.1, 0.3, 0.5, 5, 0.1, 0.6, 0.2, 0.8, minus 1, 0, 0, 0, 1, 0, 0, 0, 1. Less fun. All right. It's going to get me, so this is going to be minus 0 0.9, 0.3, 0.1, 0.3, minus 0.5, 0.1, 0.6, 0.2, and 0.2. Okay, sure. That's not looking like fun. All right. Remember, we're solving this for equal to 0. About the first thing I'm going to do is times everything through by 10. All right. Because those numbers suck. Okay. So I'm going to go minus 9, 3, 1, 3, minus 5. 3, 1, 6 to add, there was a minus sign there, 2. I'm not going to bother with, so one of the other things you'll find, your lecturer has inevitably done this, where he's done this sort of working, and he just hasn't filled in the zeros at the end, because they're zeros. They're going to stay zeros because I'm going to do row operations. Now, they suck. Which is the best one to do? All right, well, let's just do the first one. 1 minus 1 on 3 minus 1 on 9. That'll be unpleasant. But anyway. All right, so we did row 1 is equal to minus 1 on 9, row 1. And so I'm going to go row 2 is equal to row 2, take 3, row 1, and row 3 is equal to row 3, take 6, row 1. And so what I'm doing is I'm making it so that that's 0 and that's 0. Okay, loving the plan. Fingers crossed this works out. All right, so I should have minus 5 plus 1. So it should be minus 4. And I should have 1. That should also be 4. We should do the reality check on that. No, that's not right. Let's try that again. This should be, maybe do it over here. 1 minus 3 times minus 1 on 9. So that should be, this should work out to be a third. And so this should be work out to be 4/3. All right. That makes me feel a whole lot better. All right. 4/3. 4 on 4 on 3. Slick. Okay. Doing the same thing here. So this is going to be 2. And with my, this is going to be like, so it's going to be like 2 minus 6 times by minus 1 on 3. That worked out to be plus 2. So that number is going to be 4. Hey. All right. Slick. Everybody's happy about this. And then with this one, freaking symptom. Keep on telling you people, watch me. All right, just for those people playing at home, I missed the minus signs on these terms as I was writing them down. And I was going, oh, that's not right. So I'm going to have minus 2 minus 6 times by minus 1 on 9. So this is going to be like minus 2 plus 2 on 3, which is going to work out to be minus 4 on 3. Oh, minus 4 on 3. Okay. Don't need to be a genius to go, hey, the next step. This number, maybe I should write that as 1, and maybe I should write this as minus 1 on 4, 1 on 3, and those numbers are going to be 0. Because these are the negative of each other, I know they're going to work out. I'm going to do some simplification. So I've got my stuff ready to work out what my steady state vector is. I'm hoping this is going to work out. Right, so now we're going to do, I'm going to do a little bit up the top of the page so I know what I'm doing. This is saying x2 minus 3, 1 on 3, x3 is equal to 0. It's telling me that x2 is equal to x3 on 3. All right, sure. And the top line says x1 minus x2 on 3 minus x3 on 9 is equal to 0. So x1 is equal to, now I'm going to say x2 on 3 minus x3 plus x3 on 9. But because I know x2 is this, I can go, hey, that's going to be x2 on x3, 3 on 9 plus x3 on 9, 2 on 9 by x3. All right. And so my vector, 2 on 9, 1 on 3, and 1 by x3. I could actually use parameter t for x3. I could have said, let x3 is equal to t, 2 on 9, 1 on 3, 1. This is not a steady state vector for a Markov system, right? It has the property that a times the vector gives me the vector, but for a Markov process, these things are probability values and they have to sum to 1, all right? So I want sort of t times 2 on 9 plus t times 1 on 3 plus t to be equal to 1. And so that's t by, I don't know, 2 plus 3 plus 9 on 9 is equal to 1. T should be equal to 9 on number 14. All right. So my steady state vector, my vector, steady state, should be equal to 9 on 14 times by 2 on 9. Worry about that in a second. 9 on 14 times by 1 on 3 and 9 on 14. We should simplify that to be something nice. And so I'm going to write that as 2 on 14. That's going to cancel out to give me a 3. That's going to be 3 on 14 and 9 on 14. Okay, that is my steady state vector. And this describes the proportion, like at the end of the process, what these values are going to go to. Okay, did we follow what I was doing? I feel like I got everything right. For small values over everything. Okay, so what do we want to look at next? Yep, sure. Might actually go for might start a new page. All right. So, first thing, what is the definition? So back in the dark ages, when I did when I first was introduced to this concept, the lecturer did a weird thing, right? They said if I have like C1 V1 plus C2 V2 plus whatever, Cn Vn is equal to, I don't know, say Vn plus 1. They referred to that as a linear dependency. Great. Linear independence is is a set of vectors without any dependencies. All right. So, so there's a couple of things that we're going to talk about in terms of the language, right? When we say linearly independent, all right, we must be talking about some vectors, all right? The term doesn't make sense unless I'm talking about some vectors. We can actually do, we actually talk about independence of other things. But that's because we can go, hey, in a very similar way as we have vectors, we have functions, and so vectors can be linearly independent. So functions can be sort of similarly independent. All right. And so if you do much second year math stuff, they sort of talk about those ideas a bit more. All right. But it is a lack of dependency. It's saying I can't use a subset of those values to write one of these vectors. So we do that by going, actually, the set of vectors All right, so we're going to say set of vectors is linearly independent if and only if the equation, right, is equal to 0, has only the trivial solution. All right, so let's think of some, so what we normally do, so a lot of people make the mistake of saying a matrix is linearly independent, which is not true, because the term linearly independent applies to vectors, not matrices. All right, so why do they make that mistake? All right, and that is this equation lends itself to putting the vectors into, like putting our vectors into a matrix. All right, and so that's where we get those, that's where that sort of idea that a matrix can have linearly independent. A matrix, if I do my stuff with my matrix, it doesn't tell me the matrix is independent. It tells me the vectors are. And usually we put those vectors in as columns. So it's important to sort of make the distinction between the two things. Okay. So I don't know. Do I have a friendly? Oh, hey, maybe. Pause momentarily. Yep. No, what something? Oh, I think near the end, wasn't it? Ugh, they suck. Um, all right, maybe we'll do that. So if we consider the set of vectors, we will write these vectors down. I'm just going to use the ones from the question 2, part 2. So that's 2, 1, 0, 1, 3, 1, and 0, 1, 2. All right. Let's go back to Zoom. I want to look at my Zoom. Where did my Zoom go? Okay. Share screen. I want that one. Okay, I have to do that. Sure. Okay. So if we were to do this, right? So we want to do this thing here. We'd be going like C1 by 2, 1, 0 plus C2 by 1, 3, 1 plus C3 by 0, 1, 2. Sweet. Everybody happy with that. And I want that to be equal to, and it should be 0, 0, 0. Okay. If I was to write this out as equations, right, the equation I get for considering that first component would be 2 times C1 plus C2 is equal to 0. And the second component would be C1 plus 3C2 plus C3 is equal to 0. And the last one, 0C1 plus, so like C2 plus 2C3 is equal to 0. And so that's why we get, when I write this out as an equation, that should be a 2, that should be a 1, that should be a 0, that should be a 1, a 3, a 1, a 0, a 1, and a 2. All right. All right. So that linear combination of the vectors, when I expand it out and do the component-wise expression, I'm getting linear equations, and I can write those linear equations as a system of equations like this. These vectors have just become the columns, all right? If you do the hard work, you go, hey, they just become the columns. So everybody happy about that part. And so then the thing is, I want to work out the number of solutions. So I'm going to do the row operations, all right? Maybe what I'm going to do is I'm going to swap up that middle row. So swap row 1 to 2, swap row 1 and row 2. All right. So I'm allowed to swap to get a 1 in the top left position, right, when I'm doing my row reductions. Nothing says I can't do that. And so then I'm going to go like row 2 is equal to row 2, take 2, row 1. So I'm going to have 1, 3, 1, 0, 0, 0. I didn't change row 3. So I've got this, and so I'm going to have 1 minus 3 is going to be minus 2. 0 minus 2 is minus 2. Okay. More zeros. That. Oh, nope, that's not right. Beautiful. Okay. Every so often, one of the things most people go, oh no, you don't make mistakes. I make mistakes all the time. So anyone want to tell me the mistake I made when I did this? What have I done wrong? That middle number. This one here, because this was 1 minus 2 times 3, should be minus 5. Right? Mildly frustrating. So this number should actually be a 5. Good. Again, maybe what I'll do is I'll do a little bit of a swap. And I will sound like a thing. And then I will do row 3 is equal to row 3 plus 5, row 2. And so I will get 1, 3, 1, 0, 1, 2, 0, 0. And this will be minus 5, minus 2 plus 10 is going to be 8. Okay. I'm going to stop there, right? If I'm asking, are these vectors linearly independent? From that point on, I know there's a unique solution. And because it's a homogeneous system, so this tells me unique solution. So because it's a homogeneous, 0 is a solution. And so between those two things, therefore 0 is the only solution. All right. These vectors are linearly independent. All right. So that's great. Now, dodgy things I can do. All right. So sometimes that's tedious. Who thinks that's tedious? Right. That's a little bit like a pain in the ass to work that out, right? What's another thing that is connected with a system having a unique solution? Have we thought about this? So, it's really important for this that I've chosen an A that's a square matrix, all right? This is like a dodge that I can do if I have a square matrix. So you notice with my 3 vectors in R3, square matrix, I'm done. All right. All right. So if my matrix A is invertible, we would have told you somewhere along the line, this fancy thing, the determinant, tells me if the matrix is invertible. Literally, it's called the determinant because it determines if A is invertible. All right. So I might be able to go, hey, if my A, so get A not equal to 0 implies all right. So this is what I mean. I can actually use another piece of information. And sometimes calculating the determinant is quicker and easier than calculating, doing the row reduction. All right. 6 of one, half a dozen of the other, depending on the day of the week. But I'm allowed to connect. There's nothing stopping me going, hey, this is the process I'm going to do. But that's equivalent to, that process of row reductions is equivalent to finding the inverse, if it exists. Why don't I ask myself the question, does the inverse exist? And then you go, oh, well, if the inverse exists, there's a unique solution. That means those vectors would have been linearly independent. I can do that. So sometimes what we're doing is we're actually looking for, we're looking for a shortcut. All right. And so depending on the system, we may already know that those vectors are linearly independent. All right. May not. Don't know. So that would be a thing I would be looking for. The other thing that happens, all right, sometimes you can guess. All right. quite often, if my vectors are linearly dependent, all right, then they do a thing. They do a thing where you go, let's go with the first two. So if I go 2, 1, 0, and 1, 3, 1. And if I try another one, all right. Now, sometimes they do this to you. All right. Now, if you happen to have been, you would have to have been paying a bit more attention than I would expect at this point in time. But if I was to go, hey, 2, 1, 0 minus that plus 2 of 1, 3, 1 minus 2 plus 2 going to be 0. Minus 1 plus 6 going to get me a 5. Minus 0 plus 2 is going to get me 2. So what I'm saying is this is that dependency, all right? And so if I notice that, then I can go, hey, those vectors are linearly independent. Like if this was an exam question, are these vectors linearly dependent? If I was to say that, I can then go, because there is a relationship between these vectors must be linearly dependent. All right. I could say something like, I don't know, sort of maybe 2 times 1, 3, 1 minus 2, 1, 0 minus 0, 5, 2 is equal to 0 is a So I could literally put it in terms of how we've defined what linearly dependent and independent are. All right. So I'm allowed to do that. So with a small number of vectors, I'm allowed to sort of go, hey, I can see that. With other vectors, so sometimes if you're on the ball and the vectors are linearly dependent, you can actually see that dependency. So you can definitely use the fact that you've observed things to make that work. All right. So yes.
Linear dependent because one vector can default another combination by other vectors.
Yes, you can. Yes. That would be a good that would be a good way to say the same thing. All right. So yeah, definitely can do that. All right. Really linearly independent does this thing happen? All right. I do like the reason I went through that, what is a linear dependency, is because I think that helps you understand where things are. All right. So yeah. Next, anything else people want to talk about?
Sorry, one last question. Apology.
Yes.
I last lecture, like for the last week, I said when we found the linear dependent, can we just check the determinant? I remember the answer is no. Why is that?
So the reason you say no, notice when I said that you can look at the determinant, all right, is because the number of vectors and the space that they were in were the same. All right. So I have to be, so for me to be able to calculate the determinant, I have to have a square matrix. All right, and so that means the number of vectors, the number of columns, has got to be equal to the number of the dimension of the space these things in, the number of rows. All right, so only in that case when the matrix you form up is a square matrix, firstly, can you calculate the determinant, but secondly, can you use that issue of that matrix is invertible, therefore there is a unique solution. So the lecturer is saying, actually, I could have 3 vectors in R5. They could still be linearly dependent. All right. They could still meet the same criteria, but they would just be. So I actually then have to go through and be a lot more careful about what I'm doing. All right. But it is entirely possible. So because a lot of the examples we use actually have the same number of rows and columns, we can use the determinant trick.
So I'm saying the same dimension, the square matrix as the vector, but we can use the determinant.
Well, so what I'm saying is, for me to use the trick about the determinant, that matrix, that you can only calculate the determinant of a square matrix. All right. So the number of vectors has got to be equal to the dimension of the space they're in. So, you know, we're in R4, I've got 4 components. That will only work if you're asking me about 4 vectors. All right. So, so yeah, and that's, yeah. So there, yes, you have to be aware of, so some of these things with these little tricks, you have to be aware of the pitfalls, right? I can do this, but if I do that, I've got to be aware that this happens first. Okay. And that's why I was quite clear about it's got to be a square matrix before we can make that happen. Okay. Yes. Anything else? So before we move on, anything else on that linear dependence sort of thing? Everybody good? Sweet. What I should do is I should check where to put Zoom. Come on, go do the thing. Oh man. Let's check the chat. Nobody said anything recently. Right, beautiful. Okay, cool. I'm gonna put a line under that. What else do people want to talk about? Anything else? What's that? Taylor series. Sure. I thought about this and I was like, oh. Taylor series is a very, very popular problem. So, you know what? I'm going to do one of the Taylor series you should have seen. All right. And more importantly, one of the ones you should know. Okay. So, let's do, so firstly, we're going to go the series. So my Taylor series is like the sum from n is equal to 0 to infinity. The nth derivative evaluated at a, x minus a to the power n on n factorial. All right. So that's what we mean by Taylor series. All right. And Taylor actually showed that f of x is equal to Pn of x plus Rn of x, where Rnx is equal to n plus 1. There should be this fancy xi thing here. X minus a to the power n plus 1 on n plus 1 factorial. He basically showed there is a value of this between x and a that make this true. All right. And this is an equality. All right. This is saying literally this function is equal to this will be a polynomial at this point in time plus an extra term. where the only thing I really don't know is what this value is, but I know where it lies. All right. So that's one of those things. We use this particular bit to tell me how far away my Taylor polynomial could be from the value. All right. So let's just go f of x. Oh no. What are we thinking? Maybe I'll do something easy like cosine of x. All right. You are expected to know, well, I think they expect you to be able to either easily calculate or know what the Taylor polynomial for cosine sine e to the x and ln of x plus 1. You should know these things. You should. Okay, well, so when we do this, we go through and calculate a series of derivatives. Derivative of cosine is minus sine of x. F double dashed of x is equal to minus cosine of x. F triple dashed of x is equal to sine of x. And my fourth derivative of x is equal to cosine. And the cycle repeats. I need an a. I haven't thought about an a. So typically we're going to use a is equal to 0. Can't remember how you're supposed to spell Maclaurin. Anyway, so the special case when a is equal to 0 is often known as a Maclaurin polynomial. F of 0 is equal to 1. F dashed of 0 is equal to 0. F double dashed of 0 is equal to minus 1. F1, no, triple dashed. 0 is equal to 0. And F. All right. So if you're actually calculating Maclaurin or Taylor polynomial by hand, I literally recommend you do this. Calculate the sequence of derivatives, evaluate those derivatives at the value a you've been given. All right. Just a thing. All right. Do that thing. And then methinks what we do is we go, all right, well, so the thing we're looking for is like f of a plus f dashed of a x minus a plus f double dashed of a x minus a whole squared on 2. Should say 2 factorial, but it's 2 factorial is 2. So on and so forth, right? Don't want to go. So this number is 1 plus this number is 0. This number is minus 1 minus x minus a whole squared on 2 plus something that's 0 plus, and the 1 again, x minus a power 4 factorial. Now, there's a bit of an art to working out how these things go, right? But I'm going to go n is equal to 0 to infinity. I'm going to have a minus 1, and I'm going to put n in there. A is equal to 0. So x squared. This actually is going to simplify really nicely to 1 minus x squared on 2 plus x to the 4 on 4 factorial. And so I can go minus x to the 6 on 6 factorial. So I could work this out, right? So this is going to be x. So I'm going to say 2n on 2n factorial. Now, kind of notice this 2n thing happening and going, what I want to do is I want to check. When n is equal to 0, that should get me 1. And that means that sign is positive, sweet. When n is equal to 1, so to get me x squared, the sign's got to be negative, and that's going to check out. So I've just done a little checking to make sure I've got that right form. So I'm actually saying cosine of x is equal to. All right. So cosine of x is equal to. Sure, sounds like a thing. Okay. Now, I reckon just by looking at this, I can do a dodgy. I can go sine of x is equal to some n is equal to 0 to infinity. There's going to be like a -1 to the n type of thing happening. My x to the 2n plus 1 and my 2n plus 1 factorial. So because where there's non-zero, where there's zeros here, there's non-zero values for sine. I reckon I can do this. All right. That first one should be 1. So I need to go +1 to make the sign right. I reckon that's going to be right. If I just write out the first couple of terms, when n is equal to 0, that should get me x. When n is equal to 1, that should get me minus x cubed on 3 factorial. And then x to the 5 on 5 factorial. I reckon that's right. Okay. Cool. So it's kind of interesting how you've got this thing where you've got sort of x to the n on n factorial type of thing for both of these where the alternating sign comes in. All right. It's kind of interesting. If I do a trick, I'm going to do this one more. If I do a trick with e to the x around 0, because the derivative of e to the x is always just e to the x, all of the derivatives are going to be 1. So this is going to work out to be like x to the n on n factorial. So this series works out to be 1 plus x squared on 2 factorial plus x cubed on 3 factorial, and then go ... All right, so you get to see the pattern. All right, so there's some fairly, the reason we like I say, we almost expect you to remember it is that sort of thing happens. Okay, so yes, you had a question? I'm going to say no. I can't. So my gut. So I don't know. If the short version of that thing, you need to check with your lecturer. If oh, you should be. What I'd do is I'd grab sort of any ordinary calculus textbook, and they should actually, you should be able to look up. So any first year calculus textbook should have Taylor series for standard things. All right. So one of the things, right? Taylor said that f of x is equal to this series, right? F of x is equal to this series. So what that actually means is if I were to have the Taylor series for e to the, I don't know, 3x, all right? That's like a composition of functions. That's e to the x composed with 3x, all right? And so I could put it, see how x is here? I could go, well, I could just do I could just put that 3x in there. So because Taylor showed that this is an equality, all right, this thing is equal to this thing. To go from what I know to what I have, what I want to know, if I can write that in the form of a composition of functions, I can exploit that to get to calculate a Taylor series in a simpler way. All right. It can be done that way. And nothing stopping me doing, like, I could literally do cosine of x squared. And so that would be, take my n is equal to 0 to infinity, minus 1 to the n. And then this bit is just x squared to n factorial. This bit here could I could expand what that is. All right. So I could actually work out what that is. All right. So when I have something to the power to a power, I multiply those powers. Yeah. Could do that. All right. So sometimes with my Taylor polynomials, there's like shortcuts. Okay. So all right. Yes. So those are some of the dodgy tricks. The other thing we tend to do is we tend to go, hey, use the Taylor polynomial for this function to approximate this. How many terms of my Taylor polynomial do I need to have to know that whatever is within? So I might go, all right. All right. You'll often see them say about x equals 0. That value is a value of x. It's the point at which we're expanding around. All right. And so sometimes what confuses people is they go, hey, it didn't tell me what a is. It just said about x equals 0. And it's recognizing that that's telling you the same thing. Okay. And then go, let's keep it simple. E to the 1. All right. So that means all right. So if I want something to 4 decimal places, all right, 0.0000 something. I need to go, all right, so if I go 0.0001, and then I divide that by 2, because my error is like plus or minus. So I'm going to take my remainder term for 1, and I want that to be less than, the absolute value of that to be less than 5 by 10 to the minus 5. All right. So my 4 decimal places, 10 to the minus 4. I'm going to divide that by 2. So if I want it, so this can be one of the things that I always had a bit of trouble with was deciding what value I should put here. All right. So sometimes they will say within, 10 to the minus 4, 0.0001. Or they will say to so many decimal places. And so when it's to so many decimal places, you take that number of decimal places, you divide it by 2. You're halving the width you want. All right. Now, the beautiful thing is this thing for e to the x is going to look like that that bound. So we're going to go, it should be like f sort of n plus 1 derivative evaluated at 1, evaluated at, we should say xi, and then we should have like an x to the n plus 1 on n plus 1 factorial. And I want that less than 5 by 10 to the minus 5. Sweet. So far, so good. Oh, sorry. Yes. Yes. Not sure if you picked up on this, but I make mistakes all over the time, all over the place. And so being reminded to do the simple things that make it so that you can understand what I'm doing. Great plan. Now, e to the sort of xi. So Taylor's theorem says where this value lies between the a and x. So we said x is 1 and a is 0. So where xi is in the interval 0, 1. I'm going to write it as a closed interval. Now, e to the x is an increasing function. So the maximum value is at that endpoint when x is when e to the x is equal to when x is equal to 1. So this is going to be e to the xi less than e, less than or equal to e, I suppose. Now, so if we're in a world where we don't know what e is, all right, then possibly knowing that that number is e is not very helpful. All right. So what I'm going to do is I'm going to go, which is less than 3. There's a whole lot of stuff I can do to show that e is less than 3. I'm just going to say it for the purposes of this particular discussion. So you are using a bound, and we are creating a bound to help us work this thing out. And so it can be good to go, hey, I'm just going to use that number. All right. And so this equation is going to become 3x to the, this number, actually, this is like n plus 1 on n plus 1 factorial. We're using x is equal to 1. X is equal to 1. So this is just 3 on n plus 1 factorial less than 5 by 10 to the minus 5. All right. I went up rather than down. So I used an overestimate for my value because I need it to be, I want it to be less than, I'm going to get a slight overestimate for what n is. But if I want to talking about accuracy, I want to go one more rather than one less, sort of thing. Little bit of jiggery pokery. I'm going to actually treat this as an equality, and I'm going to go n plus 1 factorial has got to be greater than 3 on 5 by 10 to the minus 5. All right. So this number is like 0.6 times by 10 to the 5. All right. Which is 6 by 10 to the 4. This is like 6,000. Yeah, no, 60,000. Sweet. Hang on, 10 to the 5 is, yeah, that's right. Yep, good. 6 n plus 1 factorial. Okay, and so there is a clear choice of n. Off the top of my head, I don't know, 7 factorial is equal to 5,000. It's actually 5,040. So 8 factorial is like 40,320. All right, so 9 factorial greater than 60,000. All right, so n plus 1 is equal to 9. n is equal to 8. So I've got to have a degree 8 Taylor polynomial to get the accuracy of my estimate down to 4 decimal places. All right, sweet. Okay. Now, any questions? So the reason, so I've done the how accurate, how many terms do I need for this approximation? Because that's one of the really fun things. That's one of those things they love to ask in an exam. The other one is that trick with the composition of functions. All right. So that can be those can be interesting things to sort of ask in an exam that sort of test your understanding of what you're doing with these sort of things. Do you have more questions? All right. At some point, so I might just mentioned a couple of Taylor polynomials. All right. There's one more thing we might do. All right. We might try something. We might try one more Taylor polynomial that's a little bit more, because I want to connect. What's my last page? Okay. So f of x is equal to 1 on 1 minus x. Have we seen this one before? Because you will have seen this one before. Did you do series and sequences? Like geometric sequences? Yep, sure. So this I think is kind of interesting from one point of view. So f dashed of x. So I'm going to go a is equal to 0 again. And so we're going to go, so chain rule, the thing, so 1 minus x to the minus 2 times by the power minus 1 times by the derivative of the thing in the brackets, which is minus 1. They kind of cancel each other out. And so f double dashed of x is going to be equal to 2 by 1 on x minus 3. And f triple dashed of x is going to be 6, 1 minus x to the power minus 4. And I'm going to do another one for the fun of it. All right. And so my 4 is going to times by my 6, so it's going to get me 24. So I can actually do a thing where I'm going, the nth derivative of x, this number is 4, and this number is 4 factorial. So I'm going to go n factorial. 1 minus x to the minus. This number is 1 more, so it's like n plus 1. And I could write that as n factorial on 1 minus x to the n plus 1. All right. So if the nth derivative evaluated at 0 is actually just going to be n factorial. And so my Taylor polynomial, or the power series, is going to be equal to n is equal to 0. And so when I put in like my fn of 0, x to the n on n factorial, when I evaluate at 0, that's equal to n factorial. X to the n factorial. That bit cancels. I should put in my sum. Infinity. All right. So this is what we know about the geometric series. We actually know that this is equal to 1 on 1 minus x. Absolute value of x less than 1. All right. So we've actually done this from a different point of view, from the geometric series point of view. And so it's kind of, we're sort of connecting up geometric series and Taylor series. And so they're giving me the same thing. All right. And it's just kind of one of these nice cool bits where, hey, this bit connects nicely with this bit. Yep. All right. Are we good to go? I feel like I've talked for like an hour and 45 minutes, which I'm okay with, right? I do like the sound of my own voice. And I will happily keep talking. But do you guys, like, if you guys have got more questions, I'm going to quickly remember to bring up the chat to make sure if anyone on the chat has got, no, nobody is actually popping up on the chat. No, good. Okay. So with all the Math Learning Center revision seminars, I will scan all the notes that I've taken. I will post them online with the video recording. So if there's anything you did, although frankly, that first bit where we were talking about that first bit where we were doing what we were doing. Doing the eigenvectors, we did some things. We possibly could have got some of that right. It's some mistakes we corrected in there. So I'm like, yeah, we could forget about that. If there's anything else, Math Learning Center is open. Once exams start, we're going to go to 1 to 4, so that because there's just not that much demand after the exam start. I'm going to wish you all good luck with your exam. Come and talk to me if you have more questions in the Math Learning Center. Someone says, if you're mentioning this to your friends and they go, I wish I'd known, there is recordings. And there's a lot of other revision seminars where we've discussed other things that are available there as well. Okay? Thank you for your attention. I'm going to stop doing that. Going to say thank you all for coming. And I will possibly see you when you're doing second year engineering maths next year. All right, good luck with the exams, guys. Recording. Stop. I just want to, yes.